the building into, from stone to bricks, or change the doors, or change the roof. You can do all these kinds of manipulations. And we have an online demo that you can play with that is called Gun Paint. And if you go there, it actually will work in your phone. You can just, it will show you images that are generated by the gun, and you can scribble with your finger. You can select if you want to activate or deactivate a particular unit, and then just scribble, and you will see when it works, when it doesn't. You'll see that it's not always perfect, but most of the time it's doing things that make a lot of sense. So, you should play with that. But everything I have been talking about is about manipulating a picture that is generated by the gun. So the cool thing is that it really gives us some sense that the gun actually is learning these concepts. It's building this internal representation that seems to make those concepts very explicit. And we have evaluated also things like causality, like what is the causal relationship between the activation of a unit and the fact that an object appears or disappears on the picture. And that's how we automatically can rank the concepts that get assigned to each object, to each unit. But if you want to push forward this idea of editing images, at the end what you really care about is about editing your own pictures. Okay? You don't care about editing a picture generated by the gun. I mean, it might be nice, but it's not what you want. What if, this is a picture synthesized by a gun, but what if I want to edit my own kitchen? This is a picture of, it's not my kitchen, but let's say it's my kitchen. What if you want to edit this picture? What do you do? Well, one thing that we can do is, let's recover the random vector that if you input it into the gun, it will render my kitchen picture. And then if you have the random vector, that's it. Now you can do whatever you want to the picture. You have control. Now the gun somehow has learned, it has mapped somehow the concepts in the picture to the representation of the gun, which is kind of an object recognition task that it's doing. Okay, so let's do that. So how do you do that? Well, we can do it just by finding the random vector that minimizes the reconstruction error between the picture and the gun output. And a lot of people are working on trying to inverse guns. And you can just VIEs and so on, but let's do it with guns. So if you do that, what do you get? Well, you'll get some vector that will be the optimal vector for the reconstruction. And then if you pass that vector through the gun, it's going to give you the best reconstruction that the gun can do of your picture. So what do you get? You get this. Okay, not too bad. Let's look at the differences. So here is my original picture. This is my kitchen. And this is what the gun rendered. So can you see the differences? Okay. There is no lamp. There is no microwave. There is no plug over there. There is no window in the back. There is no stove. There are no chairs or tables. There is something there that is not there anymore. So basically, I mean, what is this? This is not a kitchen anymore, okay? It has lost everything that makes this kitchen a kitchen. So why would I want to manipulate this picture at all if it is not a kitchen anymore? So this is not going to work for me. So what is the problem? The problem is that, this is the generation process, but to put this in perspective, let's look at the actual dimensions. So the image is a almost 200,000 dimensional vector that you're trying to generate. And what is the input? It's this tiny 512 dimensional vector that has to expand itself into this huge thing. And even though 512 dimensions are very large, it's clearly, something will be lost here. It's really a tiny thing in comparison. So, if you think of the natural, we have to think of what is the manifold of natural images. So, let's say that the manifold of natural images, in this case the kitchen images, is just a slice of cheese, okay? So this is what we try to represent. Any position in this cheese is a natural image. There are some holes because the manifold has a complex topology, but what is the space of the images that a gun generates? So we want to generate something that is able to sample any point in this cheese. But the truth is that when you train a gun, what you get is something that looks closer to this. Okay, you really have a lot of holes in your cheese. And in fact, I'm being very generous by the amount of cheese that I left here. I'm pretty sure there is almost nothing. Probably you wouldn't be able to see it on this slide if I just was honest with the amount of cheese. And that's what you have. So what is the problem now? That if I have a picture, the most likely thing is that this picture is going to land in some hole in this cheese space. So I'm not going to be able to render it because my GAN can only render things that have cheese in this space. So the best thing will be some optimized random vector that will land nearby, if we do the optimization right, hopefully, and it will just render something that will look quite different from the input image. It's still surprisingly good, I must say, but really far from the original picture if you want to edit it in any meaningful way. And, if you take another picture, the same thing is going to happen. It will just land in a different hole, and your best approximation will look very different. This looks kind of better. It's still a kitchen, but it's very different. Look at, I had all these plates, and they go away. This is a disaster, okay? And, you change the brands of the... It's just not good. And even if you sample something from outside of the manifold, like a bedroom, the GAN is still happy to project it into this space. And usually just get some approximation that will look like a kitchen version of the bedroom. So, GANs are pretty amazing. So what is going on here? So let me open a parenthesis to try to get a little bit of a sense of what is being lost when we train a GAN. So what is that a GAN can actually see? Because if you want to render, real pictures, it's good to understand what is being lost in translation when you train a GAN. So we've seen that it loses all the objects. And we know that GANs have a lot of problems. We know that there is missing modes. For instance, you have these simple distributions. People have shown that when you train a GAN, some of the modes might disappear, even in this very simple two-dimensional space. So imagine what is going to happen with images. It's just going to be a disaster. And so even in these very simple problems, GANs seems to be bad. And there are several ways of improving it, but still it's not perfect. And these are very simple problems. So as soon as you deal with natural images, the entire thing is just pretty messy. So how do people know how good a GAN is? Well, there are several ways people are using to measure the quality of a GAN. One thing is just take images generated by the GAN, let's call them fake images, real images, and then just use these FID measures that tell the difference between the distributions of features computed by a network. And this is some way of getting a sense of how well the network is working. But it only tells us some measure of the error, and sometimes it doesn't even correlate with the error. But in general, it gives us some measure of the error made by the GAN. But it's not really telling us what is missing, what is wrong with the GAN. It's just giving us a number. So another thing that you can do is just render a bunch of images and see how well they look. That probably works better than FID sometimes. But these are very qualitative ways of understanding what the GAN is doing. So here is another thing that we do. So the first thing is that finding the random vector that is able to reproduce a particular image is very difficult. And it's just very difficult to invert the GAN. So sometimes you get an approximation to the vector, but it's not going to be perfect. So we define a relaxed version of the problem. First, if we want to manipulate images, and we are going to manipulate images by changing the activations of units in layer 4, we don't really need to recover the random vector that generates that picture. The only thing that we need to recover are the activations of layer 4 that will render the picture that we want. Because we know that after layer 4, the network will do the rest for us. So we can relax the problem of identifying the random vector that generates the picture by identifying the input to the layer 4 units. So in that case, it's like taking the GAN and dividing. So this is the input, this is the output. These are the different layers. And we can define another function, which is just this part that will take as input the output of the first 3 layers. So there are a number of interesting things like that come with this. The first thing is that we know that anything that the full GAN can synthesize can also be synthesized by this reduced network. We also know that anything that cannot be synthesized by the smaller network will not be possible to synthesize with the full network, because this one can do more things. There is another region where there is one thing that one can do that the other cannot do, that we don't know what is going to happen. But we know that anything that this one cannot do cannot be done by the full network. And the cool thing is that this network, if you try to reverse the activations to get the activations that you need in order to render a particular image, we can nail that one. Just a standard gradient descent with a few tricks gets you there perfectly. It gives you really, really accurate estimations of that particular input. So we can solve that problem much, much better than estimating the original random vector. So that's what we are going to do. It's an easier subproblem. Here this is an example of an input image, and this is the best reconstruction we can do of this image if we optimize the full network, finding the random vector that optimizes the full reconstruction. And this is what we get if we only optimize the activations of layer 4. It's much closer. Now, this network is capable of doing a lot more things. It has a larger space of input parameters. So now we can do a number of things, because these reconstructions now start looking really well. So we can take a bunch of original images, look for the best reconstructions we can do with the GAN, and they look so close that we can actually now run semantic segmentation, and it works. So here there are, just running standard semantic segmentations of these images, and it's able to tell us which objects are present in both images. And now what we can do is check the statistics of the objects that are generated and the statistics of the objects that were present in the original images, and just check which objects are missing. So we can do that and run histograms of counts of how many pixels were rendered that belong to a particular object class. So here, this shows the vertical axis is the number of pixels that are assigned to a particular object class, and this is object classes. Here are the names of these classes. And you can see in the blue is the distribution of the original input images. And in red is the distribution of the objects that we find in the generated images. And you can see that it follows pretty well, but there are a few changes. In particular, there are some objects that just go away completely. One of them is people. People goes, it drops quite significantly. But there are cars and fences, palm trees, signs that just go away. And there are other objects that are overrepresented, like rocks and ceilings, just things that normally correspond to the layout of the scene. So one of the things that we notice is that GANs generally have tendency to omit people. You take a picture that had people, it's clear that this image is all about the people, and this is what the GAN says. It just ignores them completely. It's not capable of reconstructing them. And it just happens all the time. Here you have a bunch of input images, and this is the best reconstruction the GAN can do, just people are completely gone. And, not just any people, anybody will delete, okay? Look, it's just gone. You have to press really hard, so you push it, okay? Eventually you start seeing something, but you need to go really strong on it. And there are some cases where the GAN actually, it really renders people. And when there are weddings, it just puts still, the wife seems to appear. But generally just people goes away. It also skips vehicles. These are the best reconstructions, and the buses, it's all gone. What is this? This is not London anymore. It goes, the signages and the text, it goes away. Nothing. No. This big sign is just not leaving even a single trace that it was there. It skips monuments. It doesn't like monuments. So here are the best reconstructions. It just doesn't like art in general, unless it's abstract. Then it likes it. It also skips a lot of detail, things that make your places. Like here, these are input images, and these are the best reconstructions. So all the decoration, everything goes away. There are just several details, but they just look very boring bedrooms. It also changes textures, because it just uses whatever it has available in the palette of possible textures that this GAN can render. So these are inputs, and these are the outputs. The textures are different. It's the same layout, but it's just replacing the sheets by something else. Maybe things looks better. I don't know. So let's close the parentheses. So it's obvious that when you take an input image, even if you relax the problem by only allowing the activations on layer 4 to represent your image, it's still not good enough. There are a lot of things that are going to be missing. So what do we do? Because I really want to change my picture, okay? So there is one possibility. What if we deform the cheese? So what we want is just to change the cheese so that my image lives in the space of the GAN-generated images. So how do we do that? this is the original problem. This is the image that gets reconstructed when I optimize the random vector. In this case, I say random vector, but it's really just the activations of layer 4. No, I'm just minimizing this problem. And this is the best reconstruction I can get. But what if we change the problem and we allow also the GAN to change? So we are going to optimize both the input activations, but also the parameters of the GAN with some regularization term, so that the parameters of the GAN don't change too much. But let's do that. So if you do that, as you add iterations, the network keeps changing, and the image starts getting closer and closer to my input image until it really nails down the image. It really looks identical. So it's possible to deform the picture. The problem now is that, well, I have changed the GAN. So yeah, it renders my picture, but will it do what I want? If I now start changing the activations of the units, will it still preserve the original functionalities that it had, or it's been lost? Because it's clearly overfitting to this picture. So this is the original image, just to show you the different reconstructions. This is if you just optimize the activations, and this is when you optimize the activations and the parameters of the network. It just gives you the exact same image. There are a lot of parameters to optimize, so it's very easy to overfit here. All the objects are back. This is a kitchen, so this is good. So, but the question is, will image editing work? And this is just the type of thing that you only know if you try it, okay? There is no theory we can write about this. So here is the picture, and I really want to put a window over there, okay? So I activate the units that are responsible for drawing windows there, and this is what happens. A window appears, but it's even more interesting. Even the reflection on the counter appear there. It's amazing. And okay, it's not always working. Okay, let's be honest about it. But when it works, it produces just very interesting effects. And most of the time, it does things. Like, let me show you some other examples. Well, some of the problems are that yes, the window appear, but there are a few other things that are not so good. For instance, here, well, there are the reflections, but oops. I think the batteries are dying here. Let me just take the keyboard. But the lamp is gone, so there are a few distortions. No, it's not. One of the problems is that the activations that we are modifying are very low resolution, so whenever you activate something, it really has an effect over a large region. Still, the window is like very sharp boundaries. No, despite that the activation mask is a little bit messy. Still, the activation, the window looks pretty nice, but it affects a larger region, and there are other things that might go wrong. So in this case, the lamp is gone. And there are several ways that you can do this adaptation. You can first tune the network to fit the image that you want to modify, and then start changing the activations, and you can do all kinds of things. And the nice thing about that is that it's really fast, because once you have overfitted to your picture, editing works really in real time, so you can do all kinds of things. There is another way of doing it, which is first just approximate the image with the original GAN, do the edition, and then optimize the GAN so that the outside of the edited mask has the properties of the input image. If you do that, then this is the output. It still puts the window inside, but anything that was outside of the mask is gone. So the lamp appears, so this is good, but the reflection is gone. So there are some interesting effects that go away. Unfortunately, when we ask mechanical Turk workers to tell us what is best, they say that this is better, this last one. But I really think that the first one is the really cool one. The other one is not very nice. But the problem is that we couldn't tell the Amazon mechanical Turks to really rate ours as much better, because the reviewers didn't like that. But I really think that this is the one, this is the direction that is really promising. So, here is the image. There are also a number of other things that you can do when you edit the picture. So, this is the reconstruction that you get when you just optimize the activations. And there are two ways that you can actually modify the GAN output in order to render your picture. So, one way is what I just described. Just modify the coefficients of the convolutions in your network to overfit to the picture. And the other way is to change the activations, leave the coefficients as they are, and just change the activations so that, again, they overfit to the image that you have. These are two different possibilities. And then you can perform editing in the same way. And what we found is that, oops, let me what we found is that if you do these two strategies, if you modify the coefficients of the convolutions, it's much better if you do it in the early layers, just after the editing. And if you change the activations, it's better if you do it very close to the image. And in fact, the best method that provided the best results according to Amazon Mechanical Turk workers is when you mix both methods. So you both modify the activations and the coefficients of the convolutions. That's what worked the best for them. So this is just a summary of what was the best. It's just optimizing the coarse layers, the coefficients of the coarse layers, and the activations of the fine layers. So now you can start manipulating real pictures. So here is a real image. And let's say that you want to put a window over there. This is the output. Just puts a window, and it looks really nice. And it even matches the perspective of the wall. So it knows a lot of contextual rules that you need to match in order for this picture to make sense. Or here is another image. And let's say that you just want to remove the chairs here. So just deactivate the units that draw chairs in that region, and the chairs goes away, and it kind of extends the wood. And the rest of the picture looks fine. So it's able to edit images that the GAN itself cannot render originally. So what happens is that we have this cheese, and now you can start even doing things with images that don't even belong to the space of kitchen images. So what if you take a bedroom, which lands somewhere else, and you do this adaptation? So what is happening is it's kind of putting cheese in that particular region. So now this is a GAN that whenever you sample a random vector of inputs, it will generate a kitchen, but there is one particular combination that it will draw a bedroom. And it will look like the bedroom. I mean, it will really look like the input image. And the interesting thing is that you can ask now, well, will I still be able to manipulate this image? So what if I have this picture and I want to put a window over there? Well, this is the output. It actually was able to put the window because there are a lot of shared properties between these two different scenes. If you use a completely different image, it starts degrading the quality of the editing. But as soon as it's able to understand enough of the scene, well, at least, this is what the intuition is telling us. As soon as it's able to get some sense of some of the properties of the scene, the rendering seems to work fine. So there is a demo that you can also access online where you can upload a picture, and it will allow you to manipulate it. And then it's trained, I think this one is trained with just churches and castles. So if you input anything else that is not within that family, the quality of what you do, it will degrade quite fast according to how far away you are in the input. But in general, it will do something fine. So you can manipulate an image and start like adding trees. You can put grass. You can change the doors, add a door there. You can put a dome there. It's not always perfect, but most of the time you'll see some interesting effects, and you can do this with all kinds of images. Like here is inserting a dome. Okay, one more dome, I guess. More dome. So, you can play with it and check the effects. It's just interesting to play with it. And you can start doing things like activating or deactivating lots of kinds of things, and eventually you start getting outside of the manifold of natural images because you're activating units in a way that the GAN never pretended to. And some of the transformations will actually work and start generating images that look kind of weird. But in most of the time, it will kind of work. So there are a number of limitations in this approach still. It's, dealing with high resolution. We are still working in 256, 256, but I think this is just, if we were Facebook or Google, probably it will be no problem. But with the number of GPUs that we have, this is the best we can do. There are a number of undesired global effects, like the fact that the lamp disappeared. I think that this is, for me, this is the most interesting type of editing. But it produces these artifacts that we want to get rid of. So eventually one day we will. And another challenge is that if you want to do real-time applications, if you have to adapt every time, it takes a little bit of time. But we have a number of tricks in the paper. So this was published at SIGGRAPH. And there are a number of tricks that allow this transformation to happen quite fast. And this is part of a global trend of people doing all kinds of image editing. So you have texture synthesis and things like a spade that goes from semantics to images, or algorithms that change the style of pictures. And this is slightly different. This is, for me, the motivation behind this was to try to understand what was the representation being learned by a GAN, and if it made any sense. So the fact that you can actually manipulate the image and have things that correlate with the semantics of the manipulations that you are trying to do I think is more evidence that there seems to be these units that are responsible of particular concepts. And what is really fascinating is that they have learned to do this with no annotations. My mother didn't have to label any images, so she can retire now. Well, it doesn't work very well, so she cannot retire right now. But in principle, these networks are actually building a representation that has semantic meaning and is explicitly represented by devoting specific units to specific concepts. It's not a distributed effect over the network. And it really depends on how you train these things. You might get the effect or not. Another thing is that the same approach can be applied to classifiers. So I've been talking mostly about GANs, but we have done the exact same thing with neural networks, just classifiers. In fact, that's what we did first. But it's just, I think GANs are a little more interesting. And they have this advantage that you can intervene on them and really check that things are really what you thought. In classifiers, it might be correlations. You don't know exactly if they have discovered a concept or not. But you can do the same thing with classifiers. So this is like an example of running this procedure on a GAN, and it gives you a description of what is the semantic representation of the GAN. You can do the same thing with COMNETs. And one interesting observation here is this is what I was showing before, the fact that semantics seems to appear in the middle of the network in a GAN. In a classifier, semantics seems to appear at the end, which makes a lot of sense because that's where you need to have access to the highest level representation to accomplish your task. But this representation, the richness of this representation really depends on what you want to do. If you want to do MNIST, if you want to train a GAN to render MNIST digits, I'll bet there is nothing interesting going on inside the GAN. Because there is really nothing interesting about MNIST. It's just 10 digits. There is really nothing you can do. There is no high-level concepts that you need to know in order to render a 2. There are strokes and things like that, but it's going to be very, very hard to know if this is really something meaningful. When you work with high-level representations, high-level tasks, the representation has to be high-level, and suddenly it starts meaning something to you. And I think that we can make sense of the representation if we work on high-level tasks. But if you work only on low-level tasks, and I will say that even ImageNet classification is too low-level because it's about objects in many cases. So what is the representation? It's going to be parts of objects, and it's going to be very hard for those parts to mean something to you, because there are many ways you can break an object into pieces. But if you are doing things like action classification, then it makes a lot more sense that the representation will be meaningful. You will have to recognize people, you will have to recognize the objects they are interacting with, and if the classifier really works very well, it will have to detect those elements. And if it's not detecting those elements, then probably it's just exploiting some other correlations in the data to accomplish the task. So we found that classifiers also build meaningful representations, and you also find units that detect faces and dogs and cars and buildings and all kinds of things. And I think this is interesting because you can start asking the question of what type of tasks do I need to have in order to build meaningful representations inside that are more interesting than the task that I'm doing. And in my group, we are working a lot now with multimodal representations. So when you mix different sensory modalities and you start building predictive models across modalities, there are some interesting representations that need to emerge. And there is a large literature of people working on the connections between, let's say, sounds and images in order to extract meaningful representations. So, for instance, one of the things is if you train kind of a GAN to go from images to sounds, and you can train this in an unsupervised way because you can take videos that already come with the RGB pixels and the sounds that are attached to that video, and you just train a system that takes as input the frames, and it should output the sounds that you should hear. That's a task that is very easy to train. Well, it's not easy to make it work, but you can train it. And for it to work, it has to understand the scene, because if you are going to predict that for a particular image like this one here, you should hear the sound of a car, this network will have to detect the car to really know that there is a car there in order to produce the sound of a car, so that that sound is coherent with the video. And in fact, we found that lots of object classes emerged inside the network when it was trained to solve this task. So I think this is a very interesting area, and there is a lot of people working in this self-supervised learning domain where you train the system to solve tasks that the training data comes from the data set itself. You don't need to collect. You don't need a human annotating anything. But the representations that are being built by the network are meaningful, and maybe they have an explicit representation about some of the categories that you already care about. So that's all I wanted to say. Thank you for being awake.
Are there any questions? Yes, please, let's start with the gentleman.
Amazing results in that talk. So one thing I was wondering, when you paint windows in that magical layer 4, you're putting in a hard activation. If you start off with like a really, really weak activation and slowly ramp it up, does a window just kind of pop in, or do you get some sort of intermediate thing in the meantime, or what happens there?
That's a cool suggestion. Yeah, we haven't done that movie. Yes, I'm going to ask David to do it just right now. Don't worry, and I'll send it to you. But my guess is that the window will not. So at the beginning, probably there will be just small perturbations, but eventually, I have no idea. I have no idea what is going to happen.
Thanks.
But it's cool, yeah.
So, gentleman in the blue shirt, please. I think.
Thank you. Very inspiring talk. So far, the GAN model only work on specific class or category only, right?
Yeah.
So what do you think about the possibility that to have a GAN that work on multiple class, for example, by some player on the Z, the random vector?
Yeah, that's a good point, and in fact, it's something we have been struggling with, because for this to be really, really cool, it will be nice that you can just input any kind of image. And people are working on that problem, and we've seen the evolution in 4 years. My guess is that in 2 years that will be solved. I think we've been also working on this problem, and it's working kind of. So I think that is just a question of the next CVPR or something.
Thank you.
My guess. There was someone.
For this stimulating talk. I have 2 questions. One question is, we know that GAN builds some kind of probabilistic model, and we have this multi-resolution expansion going from 512 to whatever the image size. Now, if you manipulate the final layer, say inserting windows, how does it propagate? Because this window needs to have some kind of a global consistency, but there isn't really a layer that would enforce it. So do you know what's happening
If
there?
you manipulate the last layer, you mean?
Yeah.
If you manipulate the last layer, you cannot insert a window unless you know how to draw it, because there are no units that are responsible for drawing the window. Those units are really in layer 4, 5, and 6. So in those layers, you can play around a little bit. It doesn't matter which layer you are. We found that layer 4 was more effective, but but if you go to almost the last layers, you cannot do the window. It's just as difficult as drawing the window yourself.
Okay, and the other question is the disappearing objects. Are they disappearing because there are no statistics? They can appear anywhere? Like people can appear anywhere, and the scale is kind of not defined. Yeah. Therefore, there is no peak in the distribution can be modeled. Is it the reason?
Okay, I don't have a very good answer to that question, but my guess is that if the GAN is really not good at drawing people, there are some objects that the GAN is really not good at, so the discriminator will tell very easily that this is a fake image. So the GAN just refuses to do it because then it's successful in fooling the classifier.
Very interesting.
I think that's...
Yeah, that's probably... Thank you.
At the right.
Okay, if I can ask the silly question, what happens if you just increase the size of the input vector so that the network isn't quite so steeply ramped?
Yes, that's a good question, and we haven't tried that We haven't tried that really because it just takes a long time to train these things, and the deadline is always too close. But my guess is that, this is my hypothesis. If you make the random vector larger and larger and larger, I think that then the effect might be more and more distributed. I think that there is something about the fact that there is this bottleneck that makes these concepts really effective, but if you make this too wide, the concepts disappear. So we have tried actually this in classifiers. So in a classifier, if you made the network just wider, what we found is that the performance at the final task did not change, but the number of objects that appear that were represented by these units was growing over time, as you made the network wider, but eventually it started breaking up.
Yeah, so it does less clustering, in other words.
Probably.
Yeah. The second sort of observation is we build multi-resolution GANs, so I wondered if that's just a way of upping the space of representation and also giving some global context as well.
Yeah, maybe. One thing is we haven't tried too many GANs with this. So we have really worked with Pro GANs mostly because they work so well. And when we started this project, that was kind of the most successful GAN. But I think that other types of GANs might have different effects, and we want to explore that. And you could try it.
Laplacian reconstruction type incremental GAN.
Yeah.
Other questions in room 104?
Yep, there's one just coming now.
There's a question from the adjacent room.
Okay.
What is it?
Yeah, hi. So towards the end, you were talking about self-supervised learning, and you said your observation is that even for the discriminative classifiers, it learns some concepts in the nodes. So my question is, are these concepts related to the image? Because this is kind of counterproductive for the self-supervised learning. Because, for example, if two different class images may have trees, chairs, and things, but they needs to be discriminated with respect to just one class, not the presence of all other classes.
Okay, so let me rephrase the question to see if I understood. So the question is, if you train a classifier, there seems to be objects that appear in the units, but you think that this might be counter-effective because maybe the objects are not very good. They are very useful for one class, but not for the other classes, and this might not be a good representation. But so the objects that appear are actually objects that are shared. So many of the objects are shared across many different categories. In this particular setting, when we train a system to recognize scenes, just to be able to tell if this is a conference room or an office or a corridor, there are some object classes that are common to many categories. So objects are really the shared elements that go across different classes, and this is why they emerge. And in fact, the objects that emerge seem to be also objects that are informative for the classes, but it's not objects that are super specific. There are a few objects that are very specific. For instance, there is a unit that detects airplanes, so that really is just going to be useful for a couple of categories. But there are many units that, there is a unit that, for instance, detects monitors, screens, and that's informative for a number of classes. So, yeah, I think it's a reasonable representation, actually. Yeah.
Are there more questions in room 104?
No, there's nothing more here.
No more questions. So we'll have time for just one or two more before we start the next session. So if you,
thanks for the interesting talk. Two quick questions. The finding of the activation units, is it by trial and error, or is there some smart procedure for finding the activation units? And the second question is, if you train the GAN with that specific unit switched off, does it the activation move to another unit, or what happens then?
Okay, let me see if I can answer both questions. I understood one, and the other one I will just make it up. So the first question was, how do we find the activations? Yeah, there is a procedure to do it. It's not trial. It's exhaustive search over all possible activations and all possible concepts and see what matches what. So the limitation of that method is that we rely on an external dictionary of concepts that we have, and we can only match units to those concepts. So if a unit is doing something that is not in our dictionary, we will not be able to tell. We have evaluated this by actually asking people to tell us what a unit is doing by showing them the images. And the correlation between humans and our method is around 80%. 80% match between the two concept sets. So it works pretty well, I think. And so the other thing is, okay, what happens in a GAN if you modify the activations, how it propagates through the layers? I think that's...
parts were still.
So
if you.
So let me say something that maybe answers a little bit your question or not. But one thing that we have checked is when you do things like, for instance, inserting a door and you activate the units, we can check how the energy of the change propagates through the layers. And if you insert the door in a part where a door could be, you see that the energy just keeps growing until it reaches the image. But if you change the region, you activate the units in a location where a door cannot be, the energy just dies out. But not immediately. It just goes little by little until it has very little effect on the output. There is always something happening, but it's just very small.
Another final question from the front row.
Okay, so I can see when you try and synthesize the domes or the grass or whatever, that's quite good. How do you deal with the window and what's through the window?
How do you deal?
Synthesize what's through the window, because you can see through the window in the context. So you showed your one where you had a window which was already in the scene, you put another one. How can you guarantee that those match up?
I think the same thing happens with paintings. What is the content of the painting? How it decides what to put there. And we haven't analyzed that. I think that most of the time when there are windows, it's just very bright. And there is really nothing that you can see through. But sometimes there are some textures that appear, but I don't know. I don't know exactly what is put in there. I don't think there is any.
Because there's so much more context outside, which is not. Got.
It doesn't really make any effort into rendering something interesting outside. I think it's generally just bright because most of the pictures in the training set, what you see through the window is saturated, so it's just white.
And how can we clone your mother to get more good annotators?
Yeah. I need to talk with her.
Okay, let's thank the speaker one more time.